Now, the third question is said a family want to install solar panels on their roof. They have 10 square meter of space on their roof for their solar panels. They use 32,500,000 joules of energy per day. A 1 meter square solar panel has an output of 200 watts in good sunlight. Now, the real question is calculate the minimum number of 1 square meter solar panels required to cover the family's daily energy use, assuming there were 5 hours of good sunlight in a day. All right. So we need to do some calculation here. Um, we want to find how many 1 square meter of solar panel will be sufficient for the family to generate the amount of energy they need per day, without forgetting that they only have 10 square meter of space over their roof. So it's possible that they will make use of all the space or lesser than the space. So which means if this space will not be sufficient for them to generate this energy, of course it will surely be sufficient because that's the question they are asking. If it won't be sufficient, they will not ask. So perhaps we should be looking at maximum of the solar panel that will be needed will be 10 maximum. So less than 10 or 10, less than or equals to 10 of the solar panel. Because 10 times 1 will give us 10 meters square. So to start with, question 3.1, let me do the working by the side. Below is fine. 3.1. Let's first find the energy that will be produced by a 1 meter square solar panel for 5 hours, given this power of the solar panel. You know that power equals to the rate at which energy is transferred. So that is energy transfer divided by time. So if we know the power output of the 1 square meter solar panel, and we know the time we are considering for it to transfer energy as 5 hours, then we can calculate the energy that will be produced by 1 square meter solar panel. So we can start from there. So to calculate that amount of energy, we know our power. So if we make energy the subject of the formula, this will be energy equals power times time. And don't forget, the unit of power was given in watts. And watts is the same thing as joules per second. Joules per second. So it simply means that when we get our energy, it will be in joule, and this time should also be in seconds. So we need to convert 5 hours to seconds. So the power is 200 watts times 5 hours in seconds is 5 times 60 minutes make 1 hour, and 60 seconds make 1 minute. So we need to multiply it by 60 twice. So we will get the energy output from a 1 square meter solar panel. And that will be, this time this is 1,000 times 1,000 times 6 times 6, 3600. So if we multiply this, that will give us 3, 6, then 5 zeros. 1, 2, 3, 4, 5. So which is 3,600,000 joules of energy. So this is the amount of energy that will be produced by 1 square meter solar panel per day, assuming that there is good sunlight for 5 hours in a day. So how many of that we will need to generate this amount of energy per day for that family? 32,500,000 joules. So therefore, we can say from here that 1 meter square solar panel will produce 3,600,000 joules of energy per day. Per day. So if we want to produce 32,500,000 joules of energy per day, how many of these solar panels will we need? So you will have to divide that 32,500,000 joules by this amount. So we can just use simple proportion. I can put an arrow here that one, I don't want to use a number again. One meter square solar panel will produce this. Now, how many 1 meter square solar panel will produce the energy that they need, which is 32,500,000 joules of energy? Let's confirm that. 32,500,000 joules of energy. So you can do cross multiplication. I'm just showing you this to understand why we are dividing this by this. So X is the number of the 1 square meter solar panel that we need. Solar panel. So X times this will give X times 3,600,000 joules. Then it will be equals to 32 times 1. This one, not this one. So that will give you 32,500,000 joules times 1. So to get our X, we have to divide both sides by 3,600,000. So X will then be 32,500,000 divided by 3,600,000. So let's do the division. So all of these zeros can cancel out. So you have 325 divided by 36. Let's use the calculator for that. 325 divided by 36. This is 325 divided by 36. So, and that is 9.0277. All right. So we have 9.0277 and so on. So this is the number of the 1 square meter solar panel that we need. But it has to be a whole number. You can write 9.02. This is the exact number. And then the solar panel, you cannot divide it. It has to be a whole number. So what this means is that, and that is the reason why they're asking us to calculate the minimum number that we need. So you may want to say 9, but 9 will be wrong because the actual amount we need is greater than 9. Even though 0.02777 looks very small, but the energy they are talking about here is huge. So if you consider 0.0277 meter square and see the amount of energy that will produce, if 1 meter square solar panel is producing, how many energy did we calculate here? 3,600,000 joules. Then 0.027 meter square will also produce a huge amount of energy. So if we say that the minimum number of solar panel they need is 9, then we will have reduced. There will be a deficient supply of energy. The energy will not be able to meet up with that family's energy need. Going to be short of. Let's calculate that. If 1 meter square solar panel is producing this amount of energy, then 0.0277 will produce this times this. So let's do that. The calculator. Oh, it's already here. So if we multiply this by 0.0277, so by 3 million, the answer times 3,600,000 joules of energy. Yeah. And let's see what it will give us. There's a mistake. Cancelled everything. We just need 0.0277, then times 3,600,000 joules of energy, and that will give 99,997 joules of energy. So invariably, the family will be short of that amount of energy if they use 9 of those 1 square meter solar panel. They will be short of 99,900 and something joules of energy. So that will not be the minimum they need. So since the number has to be a whole number, then it means that we need 10 of the 1 meter square solar panel. Even though that will produce far more than their energy need per day, but it still remain the minimum because you cannot use 9 of the solar panel. Using 9 will mean that the family will be short of energy. That is it, but to just illustrate it by writing, we just say that, let me write it. If 9 of the 1 square meter solar panel is used, the family will be short of this value multiplied by 3,600,000 joules of energy, and that gives um, just a moment, gives 99,997.2 joules of energy. Family will be short of this energy. Therefore, 10 of the 1 meter square solar panel is needed. So that is the minimum. And of course, if they use 10 of this 1 square meter solar panel, so they will cover a total of 10 meter square of their roof, and they have up to that. So that is very possible. I think that's the question they're asking next. They said, determine using your answer from 3.1 whether the family can install enough solar panels to provide all of the energy they use, assuming there are 5 hours of good sunlight every day. So we have used this assumption in the calculation already, and we arrive at 9 point something. So which means that if they use 9 solar panels, it won't produce sufficient energy for their use per day. So they need 10 of those solar panels. Given that they have 10 meter square of space on their roof, then we can determine that the family can conveniently install the enough solar panels they need to provide their energy use per day. So that's the explanation. In reality, the number of hours of good sunlight in a day varies based on the weather and time of year. Discuss the reliability of energy from solar panels compared to from a local coal-fired power station. To quickly answer this, you are asked to discuss. So a good approach is to um, look at the instances where the solar energy can be reliable and instances where it may not be reliable. Firstly, on a general note, I've said that before, the non-renewable energy source is reliable. That is the advantage. The renewable energy source, like this solar energy, is not reliable generally. But there are some instances where it can be reliable. So in places where there is irregular sunlight, like they have said in this question, maybe there's a constant 5 hours of good sunlight every day. So in such situation, the solar energy can be reliable. But in a situation where the sunlight is not steady, then it won't be reliable. Even at that, if the sunlight is steady regularly, the amount of energy it will produce is small compared to what the non-renewable energy source can produce, like the coal-fired power plants. You can also have the crude oil-fired power plant. You can have the natural gas-fired power station. So they are non-renewable energy resource. To put it simply, you just say that the solar energy could be reliable if there is a steady sunlight, as seen in this example, where there is regular supply of sunlight every 5 hours, every sorry for 5 hours in a day. Now, provided that the family's energy need does not exceed the amount all the time, it always remain the amount, and then the solar panel has its capability to produce certain amount of energy. So in that case, the solar energy can be reliable. But in a situation where the supply of the sunlight is not steady, or where the energy need of the family increases beyond um, beyond the given amounts, then the solar energy will not be a reliable source of energy as compared to the coal-fired power station, because regardless of the energy need of the family, the coal-fired power station can be used to produce electricity at any time. So the coal is present abundantly. So it can meet any energy need. And again, it's not limited by time of the day or season or whatever. So on a general note, the solar energy is not reliable as compared to the coal-fired power station. However, the solar energy could be reliable if there is a steady supply of sunlight that will produce enough energy that is needed for consumption. Also provided that the energy need does not increase beyond the capacity of the solar panel, and the hour of the sunlight does not decrease beyond the minimum required time. Thank you.